So this is the work with my advisor, Ivan Bliznets. It was already announced, so let me just begin to speak about it. Okay, so first let me explain the words happiness and what does maximizing happiness mean. Okay, so we consider some computational problem, and in this problem we are given a graph G, and some of the vertices of this graph are given some color. Okay, so we have some set of precolored vertices. So L is the number of colors, and P is the precoloring of this graph. All right. And we say that an edge of this graph is happy if both its endpoints have the same color. So it isn't, in some sense, it is opposite to proper colorings of the graph. In proper coloring, we aim to so that no edge have endpoints of the same color. This is a proper coloring, and this is the opposite. We want to maximize the number of edges having the same colored endpoints. Okay, so without the pre-coloring, this problem wouldn't make sense, because we can just color the whole graph with the same graph. So in this problem, the number of colors is important, and without the pre-coloring, it would be very easy. So smaller the number of colors, easier the problem. Okay. And on the other hand, we consider that vertex is happy if this vertex and all its neighbors, they receive the same color. And we obtain two problems, two optimization problems. They are maximum happy edges and maximum happy vertices. So can we assign colors to uncolored vertices so that the number of happy edges is at least k, or vertices correspondingly? All right, so these are our problems. And now let me give some motivation about these problems. So, okay, sorry about the scale. Okay, it is now all right. So these two problems were introduced by Zhang and Li in 2015. And these two problems model the homophily law in social networks. Homophily law states that people with the same interests are likely to connect with each other. So imagine that this graph is some social network. So these are some people. Each node of the network is a person. And these persons are connected. You can consider this as friendship. And you know that people in this network, they are in some groups. You can say that this is research groups, or I don't know, science groups, etc. And for some of them, you know their group. So here, red, green, and blue color denote different groups. And for people, for persons, you know their research group. And you would like to guess for each other person in the network their group, which group they belong to. So the reason for the problem is that the optimal answer, for example, to the maximum happy edges, will give you a good prediction about this. So in this precoloring, the optimal extension of this coloring to achieve the maximum number of happy edges is exactly like this. So you color vertices and achieve the maximum number of happy edges, and you obtain exactly that you know each group separately. So you see that each group is really, really sparse, because in each group you would expect too many connections between them. So, okay. And these are unhappy edges. They are gray if you can see it. If you cannot see it, sorry. And black edges are happy. So you can see these groups. Okay. And all vertices are happy except the vertices on the border of these groups. If I remember correctly, this model was used for prediction of which research area paper belonged to. So in the experiment, authors had some selected papers. From some large number of papers, they selected a few, and they considered it as a graph, and the edge corresponded to a citation of that one paper cites another paper. And they applied this model, so they maximized the number of happy edges in order to predict, to guess which research area a paper belongs to. And the guess was correct. It's like was I don't remember the numbers, but guess was really, really good. So this is the basic motivation for the problem. Okay, and what do we know about these problems? What is prior work? So in the paper that introduced the problems, authors gave a proof that for two colors, both problems are polynomially solvable. For one color, it is really simple. So for two colors, they gave two algorithms. For happy edges, it is quite easy. For happy vertices, it's not quite as easy as for edges, but it works. And they proved, on the other hand, that if you have three colors or more, the problem becomes two problems, become NP-hard. You can see the similarity with the coloring problem. So again, for two colors, coloring problem is really easy, but for three colors, it is already NP-hard. And of course, we consider our problem from the parameterized point of view. And for these problems, we're given simple tree-width and path-width algorithms. They are basically dynamic programming over tree decomposition and path decompositions. So both problems are in FPT with respect to the number of colors plus tree-widths or plus path-widths. Also, it was shown that maximum happy vertices is in FPT with respect to distance to threshold graphs. Then this is prior work to this. It is really recent work. We showed that both problems are doubly too hard with respect to just path widths, tree widths, or clique widths, or distance to interval graphs. So if you remove the number of colors from the parameter, as you can see in the second point here, you obtain a hard problem. And there are many other results that are not really related to our work, but we will deal with this. And what is clique-width? Briefly, you can see in this slide. So clique-width is when you construct a graph starting with an isolated vertex, then you can unite vertices, unite graphs, labeled graphs, and then join every vertex with label I with every vertex with label j, and so on. So I hope you are familiar with clique-width, but this is a brief reminder. And important here is that graphs with bounded tree widths has also bounded clique-widths. And we can go back to the previous slide and see that there are many gaps in here. For example, we can ask for the complexity of both problems with respect to the number of colors plus clique-widths. And we can also ask for maximum happy edges on threshold graphs. We also don't know about anything about its complexity. So our aim is to close these gaps. And what we achieved, we settled the complexity of both problems with respect to clique-widths. First, we showed that the maximum happy edges is an NP-complete on threshold graphs. These are graphs with clique-widths equal to 2. So maximum happy edges is an NP-hard even with clique-widths equal to 2. But at the other hand, there is a dynamic programming when you add the number of colors as a parameter. So you obtain an XP algorithm and raised to number of colors multiplied by clique-widths. And then we show that maximum happy vertices, in contrast to maximum happy edges, is FPT when you combine it with the clique-width. So MHV is FPT when you parameterize it by clique-width plus L. And at the minor result, not really related to clique-widths, we show that maximum happy vertices admit polynomial algorithm on interval graphs. Okay, this is basically our result. So we close some gaps about Clique-width for these problems, also complexity for interval graphs for maximum happy vertices, and for maximum happy edges as well, by showing that on threshold graphs it isn't hard. And what is interesting here is that this result generalizes third point generalizes the FPT results for tree widths and path widths, because bounded tree widths means bounded clique widths. Okay, and now let me go briefly through the results of this paper. Let me start from dynamic programming for MHE. It is quite easy. So we need to track edges, and they appear only when we join labeled vertices. And to count happy edges, we only need to know the number of vertices with each color and each label. So in each node of the Clique-width decomposition, we need to know the number of vertices of color and label. So we have this dynamic programming. We maximize the number of happy edges, provided the number of vertices of each label and each color. So we obtain n raised to Clique-widths multiplied by L states. And in total, with all transitions, we achieve this running time. Okay, this is quite simple, because when we join, we need to multiply some numbers. This is really easy. Okay, so the hardness results. Hardness result for MHE on threshold graphs. Okay, first threshold graphs you can see in the picture here. You can write it from the left to the right, and for each vertex you decide either it is isolated or it is connected to each vertex to the left. And we reduce from general satisfiability problem, and variables and clauses here correspond to universal vertices. And literals, literals of the formula given in satisfiability problem, they correspond to the colors in the coloring. And independent vertices we use in threshold graph, they are used to force the universal vertices to have the corresponding literal colors. In this construction, you can see that UI is the vertex either clause or a variable, and color, it is either a literal appearing in the clause or a literal of this variable. And then if we have that each vertex is colored with the literal and each clause is colored with literal, we will, because all universal vertices form a clique in a threshold graph, we achieve enough edges only if a clause receives the color of a variable of this literal. So clause receive a color of the literal. If we achieve enough edges only if a variable receives the same color, variable of this literal. Okay. This is brief explanation of the reduction. And let me go through the dynamic programming for MHV. In this problem, we need to track happiness only while performing join operation, the same with maximum happy edges it was. So basically, you had happy vertex, and when you perform join operation, a vertex can become unhappy. And the basic idea here is the following. If you have a label which has two differently colored vertices, then if you perform a join operation with this label, all vertices of the label you joined it with, they become unhappy. So you are really interested for each label, whether it has two distinct colors, then joining with it makes any vertex unhappy, or it has just one color, and then you keep track of this color. So for each label, you have L plus 1 values, number of colors plus 1. And if things were easy, we would already obtain the dynamic programming with such fields. So you would have just color label for each color variable for each label, either the color or a mark that this label have two distinct colors. But with these fields, you cannot keep track which vertices become unhappy when you perform join operation. So for two labels, you know the number, you know the color of this, and the color of this. And when you join them, you cannot know anything about which vertices become unhappy. To avoid this obstacle, you can decide for each vertex at the moment of creation. So when you introduce the vertex, you decide its color, and you decide whether this vertex should be happy. And if you decide that this vertex should be happy, then you apply restrictions on each join operator. So you cannot join this vertex with anything but the color of this vertex. So additionally to these color variables, you obtain just additional variable out. It says that you can join this label only with this color. And this, as a result, we obtain very technical dynamic programming. It's really quite technical, but ideas are quite simple. But write-up is quite long with this number of states. And this is all I had to say. This is a really brief explanation of our results. So thank you very much.
Thanks a lot, Danil. Very interesting problem. Is there anyone that would like to? We have time for let's say a very short question, and then we'll have to move to the auditorium for the closing, the conclusions, for the closing remarks. Any question for Danil?
Danil, I was just curious, how far is the study on classes and families of graphs for the maximum happy edges and vertices problem?
Okay, you mean how rich is the set of studied parameters, or?
Well, like for not in the parameterized complexity setting, like how many families have the problem been shown to be NP complete or polynomially time-solvable? Just how rich is the literature? Because this is a very recent problem, right? It's from 2015, if you mentioned it.
Yes, it is from 2015. And I would say that, so if I understand correctly, you are interested in results of the form for these families of graphs, the problem is NP complete, right?
Yeah, because for K, for at least 3 colors.
Okay, I would say it is not rich. So you can take a graph family, you can take this problem and try to prove it yourself. Yes. But I would say that the parameters are quite rich, so you can take structural parameters, and there are many results, but for concrete graph classes, it's not very rich, I would say.
Oh, okay, thank you very much.
Thank you for the question.